And it's my pleasure to introduce Michael Berry, who is no stranger to this institute. Michael Berry works at the University of Bristol and lives in the shadowy regime between classical and quantum physics, between optics and mechanics. His greatest delight is to find abstract ideas present in very simple systems, find sermons in stones, so to speak. He plays with physics just like a child plays with toys, and has the remarkable ability to look at what everyone sees. Everyone looks at and see things that no one else sees. So his work has triggered quite a lot of activity both in India and across the world in many parts of mechanics. And it's my pleasure to ask him to speak to you about Hamilton's diabolical singularities. Mike.
Thank you. Thank you very much. Well, it's good to be back after some years in this city of boiled beans, celebrating the passage of Rad, who's the ultimate free radical, through his 1,000 moons, though I can't find a sensible interpretation of that delightful phrase that gets his age exactly right. Somebody can tell me, maybe. There's nothing I can say about radicalism in science, or nature and nurture, that hasn't been said again and again and again. But I can offer some terminology that I find useful. I never contributed to high-energy physics, but I did identify a new elementary particle. It's the elementary particle of sudden understanding, the clariton. Okay. Now, we all recognize the clariton. It's the aha moment, often after long, long thinking. But alas, like other elementary entities, it has its antiparticle, the anticlariton, which comes along and annihilates the beautiful clariton that you had yesterday. You can think of the development of scientific understanding as a series of clariton-anticlariton events, hopefully with the clariton uncompensated at the end. There are, of course, mini-claritons, mesoclaritons, megaclaritons. The idea can be developed, but I don't want to say any more about it. Instead, I'm going to speak about a particular subject that's both unfamiliar and yet not in the mainstream, alongside the mainstream. It's a place I like to be, and with a very strong connection to this place, as you will see. In 2005, we all know we celebrated the World Year of Physics, marking the centenary of Einstein's discoveries. But there was another anniversary that year. It was the bicentenary of the birth of Hamilton, William Rowan Hamilton, born in 1805 in Ireland. Now, that was an anniversary also worth marking. I mean, just consider how deeply embedded the name of Hamilton is in our culture. Consider the following Hamiltonian. How often have we read that? Okay. Well, here he is. And what I want to do is to tell you about the phenomenon that made him instantly famous. A prediction. It's the phenomenon in optics called conical refraction, which was studied occasionally down the many decades, and recently it's become intensively studied again, and we realize that there was a lot to understand about it that wasn't understood then, and it's now more or less a completed subject, and it's a story I want to tell you. Now, what did Hamilton teach us? Well, his contribution was to think in mechanics of the trajectories of particles and in optics of the paths of light rays in a common framework. And a tool that he invented for that we call phase space, where you consider position and momentum on a similar footing. Now, momentum in many, many applications simply amounts to direction. And so what he taught us was, in 3 words, he took direction seriously. Now, I don't know if you had the same experience as me, but when I first learned Hamiltonian mechanics, it seemed very artificial to me. After all, most of the forces you encounter in nature depend just on position. refractive indices in optics depend mostly on position, air to glass, water to air, water to glass, and so on. So it seemed a bit artificial to treat position and momentum, direction, in the same footing. However, in the optics of crystals, the refractive indices depend essentially on direction. Crystals are essentially anisotropic, at least many of them, and it's natural then that Hamilton would have found the perfect application and illustration of his new ideas in crystal optics. So let me remind you a little bit about that. It's something in this place very well known, but I have to nevertheless take you through it. In polarization optics, you have what was known before Hamilton, that in any direction in a transparent material, two waves can travel without change. And they're polarized at right angles, and they have different refractive indices, different speeds. So here you have the two waves traveling with two orthogonal polarizations. Now, a tool that had been developed by Fresnel to describe some of the direction dependence of these, of the speeds in particular, is the wave surface. And that's a polar plot of the refractive indices on direction. So you choose a wave going in a particular direction, there it is, and you go out in that direction and you mark the two refractive indices. Well, of course, as you go from direction to direction, this gives you two surfaces, and the shapes of those surfaces was much studied. Now, there are lots of special cases, or several special cases, which I won't go into, except say the trivial case is if you have an isotropic material, like water, for example, then the surfaces are two coincident spheres, and it's an empty construction. But Hamilton was concerned with the most general case, and all three directions then are different. A common crystal used in those days was aragonite. It's a version of calcium carbonate. And there you have one of the surfaces which is dimpled and one of them which is bumpy. You can't understand this structure unless you put them together and slice the figure in half, and then you see this structure, and you see immediately that you get intersections at 4 points on two optic axes, and these are called biaxial crystals, and it's the general case. Now, Hamilton did what his predecessors did not. He immediately zoomed in on the intersection. Nowadays, we'd see this as a singularity of the surface, or the pair of surfaces, and he wanted to understand what happened there. Each intersection is a double cone, a diabolo, and so this is Hamilton's diabolical point, or Hamilton's diabolical singularity. There it is. The optic axis goes aslantwise through it. That slantness is an awkwardness in all calculations, and it will appear from time to time, but I don't want to go into it. Now, he knew another thing from his predecessors. He knew that in a crystal, the wave direction, that's perpendicular to the wavefronts, is not the same as the ray direction along which energy flows. They are the same in an isotropic material, but not anisotropic. And here's the wave direction, for example, and there's the ray direction. And he knew the law which gives you the ray direction. It's that the rays are at right angles to the wave surface. So here's the wave direction, and there's the ray direction. He knew that. By the way, we now call this Hamilton's first equation. It relates the velocity to the gradient of the Hamiltonian, which turns out to be the normal to the wave surface. Well, since there are two sheets of the wave surface, there are two rays corresponding to every wave direction, and that's why this whole subject was called double refraction. But he realized that things are different near the conical intersection, near the diabolical point. There, the wave cone generates a complementary cone of infinitely many rays. This was his realization. So here's the wave cone. It's normally very flat, at most a few degrees for common, almost all, indeed, anisotropic materials. That means that the ray cone, perpendicular to it, is very thin. Okay. And there's the axis. It's a generator of it. Well, then he realized that this would give rise to a very interesting, unprecedented, indeed, phenomenon. If you take a crystal slab and you cut it at right angles to the optic axis and send a narrow beam of light in, there it is, this would spread into a cone, hollow cone inside the crystal, and when it refracted out, it would give you a hollow cylinder of light, which you would see on a screen as a ring. This prediction was immediately taken up by the Reverend Humphrey Lloyd, who was much taken with it, his colleague in Dublin. He said, "It's in the highest degree novel and remarkable. Singular and unexpected consequences of wave theory, not only unsupported by any phenomena hitherto noticed, but even opposed to all the analogies derived from experience. Astronomer Royal, Airy, not noted to be a generous man, perhaps the most remarkable prediction that has ever been made. Herschel, theory actually remanding back experiment to read her lesson anew, informing her of facts so strange as to appear to her impossible, and showing her all the singularities she would observe in critical cases she never dreamed of trying." Now, why this, what sounds to us like hype? Well, it wasn't, because I think that this was, if not the first, one of the first occasions when mathematics was used to predict a qualitatively new phenomenon. Now, of course, from Galileo, from Newton, Laplace, Lagrange, it was known that mathematics is a way to describe accurately the natural world. But the phenomena that were described, the tides, the motion of the moon, eclipses and so on, were known phenomena. And here was something completely qualitatively new. We forget how surprising that was. Nowadays, as theorists, if we have some theory, the first thing we do is we say, well, in these equations, what is new here? But it wasn't a familiar idea. I think that's the reason why people were so astonished. And when Humphrey Lloyd did the experiment and found this ring, then this created a sensation. It made Hamilton, the young Hamilton, immediately famous. Now, I'm going to show you lots of pictures like this, red pictures. All of these pictures were experimental pictures made in my little laboratory in my house, either by me or my student, Mike Jeffrey, and that's a story I'll tell in a little while. Humphrey Lloyd points out very eloquently how usually you don't get the orientation right. You shine your incident beam and you don't quite get the diabolical direction, and then you see double refraction. But in the last fraction of a degree, as you orient your beam relative to the crystal, double refraction turns into conical refraction. It's a very dramatic thing to see. His ring was a few millimeters in diameter. Okay, there we are. Now you see something there which Lloyd didn't see, but which Poggendorff saw shortly afterwards. You see that actually it's a double ring, not a single ring. Now there he comes. There's Poggendorff. Doesn't look very happy. Probably was happier when he... 1839 is when he did the experiment. That was the beginning of photography, so this picture was taken decades later, probably. He found these two rings, separated by a dark ring. It's called the Poggendorff dark ring. It was observed by Potter about the same time, but it's called Poggendorff's. Just one phrase in a very short paper, just one paragraph, a bright ring that encompasses a coal black sliver when you translate from the German. Well, here we are. Whoops, where is it? There we are. And there we are again. You see them more clearly. Now, that was not explained, that dark ring, for a very long time, not for 65 years. In fact, by Waldemar Voigt, by the way, in the same volume of Annalen der Physik, where Einstein published his famous papers. Now, what was Voigt's reasoning? That Hamilton had assumed an unphysical idealization, a perfectly narrow beam traveling in one direction. Now, from wave physics, you know that's impossible. The narrower the beam, the greater the angular divergence. The more you squeeze, the more you spread. When I made these pictures, I was reminded of my mother. She was a dressmaker. And when I was a child, women would come to the house to be fitted for wedding dresses and the like. My mother often commenting disparagingly on the state of their underwear. In those days, women wore corsets, and it was clear that the more they squeezed in one place, the more they would spread in another. Now that's conservation of volume. This is conservation of phase space volume. Nowadays we call it Heisenberg's uncertainty principle, but it's the same phenomenon. Anyway, it has consequences, as Voigt realized. It means that you want a narrow beam. Okay, why do you want a narrow beam? Because if you have a broad beam, you'll blur out the little ring that you're trying to see. You want a narrow beam, but that gives you an angular divergence. It can't simply hit the diabolical point, but it must explore a small neighborhood of directions around it. So here we are. Let's look more closely. There's the contribution from beam directions away from the diabolical point, a little ring. And you can now see immediately, it's just the little area element in polar coordinates, that the closer you go to the diabolical point itself, the smaller the contribution from the range of directions. And hence, at the diabolical point itself, it's nothing. And that's the explanation of Poggendorff's dark ring, which he gave qualitatively, and the quantitative explanation didn't come till many decades later. We'll see that, indeed, until this century. Now, here's something else. Lloyd observed that the rings are polarized, linearly polarized. And moreover, the direction of linear polarization changes, rotates by half a turn as you go around. Of course, it can do that because polarization isn't a vector. This polarization is the same as that one. He observed that, and very generously, you wouldn't see this so often nowadays, he wrote, I noticed that this phenomenon, it doesn't appear anywhere in Hamilton's paper, but I'm sure he knew it, he wrote. Anyway, there we are, and here are the polarizations, linear polarizations. Now, I think this is the first geometric phase, actually. Mathematically it is, I won't go into that, but so there's Humphrey Lloyd identifying this phenomenon already in 1832. It means, for example, if you take linearly polarized incident light, this picture you'd get for circularly polarized. If you take linearly polarized incident light, you wouldn't see the whole pattern. If you take, for example, vertically polarized light, you just see this loon shape, and indeed you do. By the way, another little aside, we realized a few years ago, Mike Jeffrey and Masoud Mansouripour and me, that this has interesting implications for the angular momentum of light. Suppose you send in circularly polarized light, the photons are all their angular momentum is all spin angular momentum, to do with the polarization. Orbital angular momentum is to do with the spatial structure of the field. So what this does, this crystal, it converts pure spin angular momentum to pure orbital. And by the way, what comes out is exactly half what goes in. So there's a little tiny torque on the crystal. I think it's too small to measure, but that's just an amusing aside. Now let's continue, and now we come to this place, and this gentleman who some of you know, there he is there, in the year of my birth, he studied this phenomenon. He introduced a very important ingredient into the study. Notice the long time scale of developments in this subject, many decades between each one. He realized that because of diffraction, the pattern you see beyond the crystal depends on where you put the screen. And he realized that if you put the screen very far away, or as he observed and explained, that the rings fade and they're replaced by a central spot. There it is. In the experiments, you see there are some rings. We'll discuss them later. And understand where they arise. Well, he explained that in terms of the turnover of the cones slightly away from the diabolical point. You see, there's the structure. I'm rotating it, magnifying it, and you see there's this turnover, and there are these two places where the rays are forwards, directly forwards. Well, there aren't just two. There's a whole ring of them. And that means that, in fact, there are infinitely many rays in the forward direction. There's a forward caustic, an axial caustic, and that's the spike that he sees. That was very nicely described by one of the, I think it was Graves, who wrote about Hamilton, somewhat as a plum can be laid down on a table so as to touch and rest on the table in a whole circle of contact. An unobvious geometrical feature of this wave surface. Hamilton had noticed it, actually. He wrote about it. And Airy, by the way, wrote, oh yes, I'd noticed that too. I didn't think it was very important. Anyway, that's the explanation of that. Now, 1978, another nearly 40 years, in Belarus, they thought, look, let's do this theory properly. You have Maxwell's equations, let's really start and get the theory properly. And they realized that conical refraction is a wave problem. I call it conical diffraction, actually, nowadays. And the details of the rings depend on, for example, on the profile of the light that you send in, whether it's a laser like we use nowadays, or a pinhole as he used, as Raman used, and as people before used, going right back to Humphrey Lloyd. And they gave a definitive formalism. I rediscovered it, not realizing, and, but it's really theirs. Now, Bloomberg and Schell, about the same time, also did some experiments, and they also gave a theory, but actually their theory was too elaborate. I'll explain that in a while. So they didn't actually, although everything they did was correct, and they compared with the experiment and so on, they missed some essential features which you only see with a certain simplification. Now, Warnick and Arnold, another 20 years later, noticed in numerical computations using the Belsky-Kapeluk that there were faint secondary rings within the inner Poggendorf ring. There you see some of them, and here in our experiment you can see some of them. Actually, the contrast on this screen is not as good as on my screen. Well, we just have to live with that. I'm sorry about it. There's a bit of overexposure. Okay, well that's that feature. So now let me spend a few slides on the theory before going into the experiments. The simplifying feature, which Belsky and Kapeluk raised, all the angles are small. You can use paraxiality. Cos theta is 1 minus a half theta squared. The next term gives errors which are less than 1 part in a million for every experiment that's been done so far, so it's quite safe. Then there's a simplification. I'll tell you what it is now. Look, here's the setup. You've got the beam coming in and the crystal and the cylinder coming out. It helps to measure radial distances in terms of the width of the incident beam, or the pinhole, whatever it is. So that's a dimensionless row. It helps to measure longitudinal distance in terms of the Fresnel length, measured from the place, usually inside the crystal, where the waist of the beam or the pinhole would form an image if the crystal were purely isotropic, as it almost is. These are small effects I'm talking about. So that's that. K0 is the wave number of the light that's sent in. And then you measure the radius of the cylinder that comes out, rho 0, in units of the width of the beam. Now this rho 0 is the single parameter that governs the whole theory, the whole pattern. And it replaces these 5 quantities, all of which the 3 refractive indices, the thickness of the crystal, the width of the beam, which you would need if you don't make the paraxial approximation. So it's a lot simpler. It's a 1-parameter family. And the conical ring detail emerges in the limit as rho 0 gets large. In the experiments I will show, it's about 60. I told you that you need to have a narrow incident beam, otherwise you blur out the structure. Well, that means that rho 0 must be large. Okay, then what's the theory? Well, you write the transverse electric vector, D vector, as a superposition of coupled plane waves. That's what a beam is. So, for example, you have the Fourier transform, kappa, sideways Fourier transform of the beam. Let's say, for example, it's the Gaussian. Call it A. Right. Then, here's the theory. The wave that comes out it's a vector, something times the polarization of the light you send in. I'm assuming it's uniform here, but it's not difficult to generalize there. And of course, what do you need to multiply a vector by to get a vector? A matrix. And here it is. Now, the first involves the unit matrix. The second involves a couple of the Pauli matrices. This is my way of writing their theory. It's a simple way. And then there are these 2 integrals, which are these Belsky-Kapeluk things. And these are integrals. They involve where you are, rho and zeta, and your parameter, rho 0. Now, these are and they involve, of course, the structure of the beam, incident beam. And these are, you just can't quite evaluate them analytically. You almost can, but not quite. But for circularly polarized or unpolarized incident light, the intensity that you would see is just the sum of the squares, absolute squares of those two integrals. So you can calculate. And you can see by numerical calculation, for example, the rings transforming into the spot as you move away from the crystal. And here's a picture that shows all the phenomena. Here's the Poggendorf dark ring, there it is. Here's the 2 bright rings, and the axial spot just beginning to come, this Raman spot, and then these secondary rings found by Warnick and Arnold. So all the features are there in the theory. Well, you can do a lot of analysis using this formalism. For example, you can do geometrical optics, either from Hamilton's principle or by taking those integrals and using the method of stationary phase. It's a standard procedure. And for Gaussian incident beams, here's the answer. And I want to show you one point only. Look, this modulus of rho minus rho 0 shows that this contribution is actually the main one, vanishes exactly on the ring that Hamilton identified, and this is the theory of the Poggendorf dark ring. It's an anti-caustic. It's a place where the mapping, the Jacobian between the instant and final, is zero and not infinite as it is on an ordinary caustic. And you can see now, as you go away from the crystal, how the rings separate and eventually the central spot appears. Compare that with the exact theory that you can compute without much difficulty, and it agrees fairly well, except that you don't get, in geometrical optics, you don't see these Warnick-Arnold rings, and when you do the analysis, you can identify what they come from. Of course, they're interference, but they're interference between one of the geometrical rays and a diffracted ray scattered from the singularity, the diabolic point in momentum space. That's where they come from. Now, you can do more. If rho 0 is large, you can concentrate on the region near the rings are, where the rings are. And you can do a full asymptotics and for the structure of the rings themselves, very, very close by. And at some function, some function of distance from the dark ring. And for a Gaussian beam, it's some, never mind, some combination of Bessel, doesn't matter what it is. But you can calculate it, and that's the structure of the two rings with the Poggendorf dark ring that you'd see, all this to be compared with the experiment for the most focused rings, that is, the rings in this focal image plane, where this distance parameter zeta is zero. So the place where, for an isotropic crystal, the place where where you would get an image of the incident beam, say it was a Gaussian, you see a little Gaussian. This is the same thing you show children, where you take a glass of water, you put a coin in the bottom, and the coin appears higher up. It's that place. Instead, you'd see the rings with this profile. And why I'm showing you this is that to illustrate that the structure of the beam matters. If you use a pinhole, then instead of Bessel functions, you get elliptic integrals, never mind that. But you get this rather astonishing pattern, which has actually never been studied, and that's a prediction to see this rather interesting. But of course, the origin's way over here somewhere, the center. But this is the profile of the rings. It's a very interesting pattern that one would see in the focal image plane. Of course, that's often inside the crystal, but that doesn't matter because with a lens you can project it onto a screen. Okay. Now, finally, for the theory. Looking now at this Raman spot far away, there are those little fringes. And they're interference fringes too, between the two geometrical rays. Now, how can that be? Because they're orthogonally polarized, and orthogonally polarized rays don't interfere. Well, these are interference between one of the rays and the first correction beyond geometrical optics, and they're no longer orthogonal, so the interference is very weak, and it's the sum of the squares of two Bessel functions. I don't want to go into the details of this picture, except to point out that when you do go far away and you scale right, the rings are actually shoulders. They're flat inflections at the zeros of the first Bessel function. Again, something to test, we'll see. Now comes the experiment. I'll tell you a story. You see, up till now was development of this Belsky-Kapeluk theory, and I'd written a paper about it in 2004, and I visited Dublin. I met James Lunny, and he said, do you know it's Hamilton's bicentenary next year? I said, no, I don't know. He said, have you heard of conical refraction? I said, I've just written a paper about it. He said, would you like to see it? Now, we theorists are pathetically grateful when anybody shows us anything that's related to what we do. I said, well, I'd love to. And so he took me into his lab, and he had a crystal. I'll explain where he got it in a moment. And I said, have you heard of the Poggendorf dark ring? He said, no. Have you heard of the Raman spot? He said, no. Have you heard of these Warnick interference? No. Within 5 minutes, we'd seen all these things. It was a fantastic moment. And I determined I must have one of these crystals myself. And he said, where do you get it? Where do you get it from? And he said, there's a company in Germany, VCT Technology, whose main business is crystals for nonlinear optics, laser physics and so on, to celebrate the centenary as a marketing opportunity, they've made crystals for conical refraction. And when I learned where they were located exactly, I determined that instead of ordering it online, I would go there and collect it. And the reason is that these crystals were made in outside Hanover, beneath the green fields in an old nuclear bomb shelter. It was the nuclear bomb shelter of Deutsche Telekom, which would have been, had there been a nuclear war between Russia and the West, it would have been the communications center between NATO and London, Washington, the Warsaw Pact as well, probably. But they sold it off. They decided it was no longer necessary. And it's perfect for growing crystals, of course, because it's underground, constant temperature. There are beds of sand of different thicknesses, to remove all possible particles from the air. So it's very good for crystal growing. And they made this crystal. So I went there and I bought my crystal and took it home. And with my student, James Lunny, Mike Jeffrey, we decided to see how good it was. And it turned out that the crystal was actually much better than the two that James Lunny had bought. And by the way, they only ever sold 3, 2 to him and 1 to me, so that was not a very successful opportunity for marketing, but never mind. But ours was better. So much so that we could do quantitative tests rather than just demonstrate the phenomenon. And there's what I showed you before. And we obtained, row 0 was about 60, and we focused our beam down to about 7 microns. Okay, so good. And we then broadcast, we magnified the image and put it onto a screen and took photographs of it. The zeta was a bit hard to measure, the z, because each time you change, you only have to change actual distance by a couple of millimeters to change this distance parameter by 1, and a lot happens in 1, but still we could do it. So here we are. Now this is the theory for a series of patterns that we would see. And here's our observations, and you know, they agree pretty well, not exactly, but fairly well. Now, the beauty of modern technology is that theorists can pretend to be experimenters. You see, with the digital camera, I could just take pictures, we check the linearity and so on. That would have demanded image capture equipment that would have cost thousands of dollars a few years before, but my little digital camera did the job. And moreover, having the JPEG, and you can import it into Mathematica, you can do image processing of, again, the kind that you would have needed very expensive software just a few years before. So in particular, you could circularly average and compare the profiles with observation. Now, these are our experiments, and you know, they don't agree perfectly here, and the oscillations aren't quite perfect, but we were able to still make some measurements. So, for example, the Poggendorf ring, the distances between the 2 bright rings and the central ring and dark ring and the outer ring as a function of distance. And that agreed fairly well. We could measure the width of the first interference fringe as a function of distance, and that worked fairly well. And at greater distances, we could measure those weak diffraction rings surrounding the Raman spot, the first 2 of them, and there, once again, we got good agreement with observation. Now, we just play. I mean, we're really theorists, but James Lunny and his colleagues in Dublin, real experimenters, and they could, for example, test very precisely this formula for what happens in the focal image plane, these sharply focused rings, and there's their comparison of experiment with theory. And they could also check more precisely at the other extreme, very far away, these diffraction fringes. So, I mean, these Bessel functions are the combination of 2 the ring intensity is the sum of the squares of 2 Bessel functions, but by carefully choosing instant polarization, you can separate those out and get the 2 J0 and J1, and they could see, except far away where they wouldn't expect the theory to hold, that it works, again, very well. So that's all nicely understood, and there are some more experiments now. There's a group in Dundee, Edith Rafailov and Amin Abdolvand, and this is all pretty well understood now. So far, so good. I want to point out that when I was here before, I met, is Rajendra Bandari here? Are you here? He's not here. Okay. Well, I learned something from him that we wrote about afterwards. You can do all this yourself very easily. Not all this, sorry. You can demonstrate the effects of biaxial anisotropy, not conical refraction, because that's hard. That needs quite a long crystal. By the way, I should have said something. what I learned from James, before I go to this, what I learned from James, let's go back a bit, what I learned from James Lunny was this. Just as the theory had developed very slowly over the many decades, so likewise experiments did. And the reason is that they're difficult. Aragonite apparently is hard to grow, and almost all the crystals you can grow are a lot of imperfections, and you need about an inch worth of crystal, I mean 20 or 30 millimeters, for the ring to be big enough to see it. It's actually quite difficult to do, and that's why the experiments were so slow. Even Bloomberg, master of crystal optics, of course, especially nonlinear, he says, we got our crystal from the private collection of somebody or other. So, you know, it's not that easy. Anyway, it's much easier, however, if you have a thin film. And this was based on the following idea, which you see in any mineralogy textbook. Going through the crystal, the two waves at different speeds, they get out of phase, and using what we came to call a black light sandwich, you can see the various phenomena associated with the cones by interference. And so here it is. You have two polarizers at right angles. You see this in Born and Wolf as well, or Landau and Lifshitz. Two polarizers. Now, what you put inside, now, by the way, this is the bread of the sandwich. Okay. Now, the filling of the sandwich, well, you want a biaxial crystal. You know, I thought for ages as a theorist, how could I ever find one? But Rajendra Bhandari pointed out to me that we'd been familiar with such a material for many decades, namely overhead projector transparency foil. You know, for 30 years, I don't know if you have one here, I don't see it. In many lecture rooms, dusty and unloved, this what's called legacy technology. And it didn't realize that all the time we used it for showing that the material is biaxial anisotropic. Almost all the different kinds you can buy, the ones you use in a laser printer, the ones you use in an inkjet printer, the ones you write on, they're all biaxial anisotropic for reasons that no optical scientist other than Raj Bhandari had apparently realized. But when I told my polymer physics colleagues, they immediately understood why it must be so, because of the way they're manufactured. But anyway, when you do that, and just look through, you look, what's looking? A couple of years ago, I wrote a paper on looking. Looking means that your eyes in a particular place and you direct your gaze in a particular direction. That's, of course, impossible by the uncertainty principle. So, in fact, you see something called the Husimi function. Never mind. You see light from different directions, and so you see at each point in direction space interference, and the interference are between the two waves and the two sheets. And so what you're seeing near the you see interference fringes, you're seeing contours of constant separation of the two sheets of the wave surface. Okay, and here are the bullseyes where the diabolical directions are, the optic axes. Just two of them, the other two are behind. And you even see this black brush, and for an argument I'm not going to give, that's a consequence of this polarization geometric phase, this sign change as you go round. So you see a lot of features. And if you put one of these in front of your camera, then anything you take a picture of will be decorated by one or two of these points. And in particular, here's the sky outside, in the garden outside the place where I work. And you can see, they're coloured, of course, because it's an interference phenomenon, it's white light. And there you see, you learn a lot from this, by the way. I give a whole lecture sometimes on the properties of matrices that depend on parameters, using just this picture to illustrate the different phenomena. And this point is the degeneracy of the matrices. You see, you learn something else. It was a clear day. This is the blue sky, but all the colours are there. So you learn something also which was known, that the blue sky actually is very, very unsaturated. It's almost white. We see it as brilliant blue. That's our brains. But actually all the colours are there, and so there you see. Now, we have developed this subject considerably, and the reason is, when you think you understand something, we all know, that's just the beginning. Then you realize there are whole directions you can go in, springing off from there, which you don't understand. And there are several generalizations of Hamilton's conical refraction which radically alter the underlying mathematical structure. And two of them I've explored with Mike Jeffrey, and the recent one just now I'll tell you about later. Now, what's the first? You can incorporate optical activity. Optical activity is microscopic chirality, handedness, crystal lattice different from its mirror image. Again, much studied in this place by one of my intellectual heroes, which was the young Pancharatnam, together with his uncle, old Raman. Well, what happens then, it's known, the diabolic points get smoothed away and the cones separate. Mathematically, it turns out that you're seeing these, they're the eigenvalues of a 2x2 matrix, which instead of being real symmetric is complex Hermitian. That's what this chirality does. And you need two parameters to get a degeneracy of a real symmetric matrix. And you have to, because you have direction. So that's why you see the conical intersection. That's what Hamilton's point is, actually. But when you have a complex Hermitian matrix, you need three. This is called the Vigna von Neumann non-crossing theorem. Well, you don't have three, you only have two. So you don't have a degeneracy. You have a separation. And what was the consequence of that? It's very dramatic, actually, and never been seen, and there are experiments that should be done. Well, let's look at the geometrical optics first, and let the chirality be represented by some parameter sigma. So here is what happens, what I've told you already in an unfamiliar picture, if you have no chirality. Here are the rays coming out, here's distance from the crystal, the dark ring here, here's the dark ring, here's the Raman spot beginning to come, Raman spike. If you add chirality, immediately you get something much more dramatic. You get a caustic, a cusped focal cone springing out from the Hamilton-Poggendorf ring. And the height of the cusp is 1 over sigma, so it recedes to infinity as you switch off the chirality. It's a very singular limit. But that's the phenomenon. Now that will be an interesting thing to see. If you use poor person's geometrical optics, poor person's wave optics rather, you just take the geometrical rays and you put phase on them and let them interfere, you get a pattern which is fairly accurate everywhere except on the caustic itself where it fails. But you can also write the corresponding theory, those integrals, they're slightly modified, and there you see this pattern. Now, it turns out that near the cusp itself, and this focal spot here, this is a rotated cusp, you can give a local description of the field. It's called the besoid, or the spun cusp approximation. And so all of this is structure that remains to be seen, and it will really be lovely to see it. Now, the second thing you can do is incorporate absorption, also studied here in those old days, although not in the context of conical refraction. Well, absorption is likely to be anisotropic too. That could be quite a complicated problem because the axes of anisotropy of the imaginary part of the refractive index are usually different from the principal axes of the real part, and you've got lots more structure. Well, then it turns out that the cones split into a wave surface with the two sheets connected at branch points. So instead of a diabolic point, you get two branch points. So there we are, connected. And what does that give rise to? Well, you can quantify the absorption by a little 2 vector. It's the non-Hermitian traceless part of a 2x2 complex symmetric. Never mind, doesn't matter what it is, little vector. But then, how do you choose which direction to look at? You see, you choose halfway between the two branch points. They're called singular axes. I were identified by Voigt long ago. Or do you choose halfway between? What do you do? Well, you don't. You let the direction be arbitrary. You can choose where to. And then a very interesting thing happens. It's a surprise, at least for Gaussian beams. The effect of both misorientation and absorption, anisotropic absorption, that's 4 numbers, can be captured by a single variable. And there it is. And so what this means, what this means is that the effect of absorption is the same as the effect of misorientation, which we know, apart from some overall exponential decoration, which I won't go into, which and we know what the effect of misorientation is. It converts conical refraction into double refraction. We've seen it already. So that's a surprise. And for Gaussian integral, the only effect is to complexify the radial variable in those Belsky-Kapeluk integrals. Instead of rho, you get psi and eta, the x and y, plus I times u, and then everything is the same as before. Well, that's interesting. It's kind of surprising, but the effects are very profound. Now, what I've shown here is the exact and the geometric optics, which, again, you're introducing absorption or misinclination, which is the same thing as I've told you. The only difference is you don't see this little fine remnants of the Warnick-Arnold rings. Otherwise it's the same, you think. But then you look more closely there, and if you plot the intensity logarithmically, so you see very fine, faint structures, you see something very, very different. It doesn't come out very well on this screen. But what you see is a dark ring of geometrical interference with dark spots of complete destructive interference, which you can see, look at in more detail. And what these are, very interesting, these are interferences between geometrical rays. The rays are now complex. The rays, the polarizations, are eigenvectors of this little 2x2 matrix. But instead of being orthogonal, as they are when you don't have any absorption, for a non-Hermitian matrix, the eigenvectors are not orthogonal. And therefore you can get interference between them. And indeed, sometimes the interference can be total, and that's an effect, non-Hermitian mathematics showing itself up in this diffraction. Lots to see here. None of it has been observed. And actually, it's very hard to, we would like to be able to tell the experimenters, you know, take this crystal and you will see the phenomenon. But we hit a problem. We wanted, you see, what you want are several numbers. You need, for a particular crystal, look up in tables to find the 3 principal refractive indices, the 3 real refractive, the 3 imaginary parts of the absorption, and the 3 numbers which give the rotation between the 2 sets of principal axes, 9 numbers. For orthorhombic crystals, the 2 sets of axes coincide, it's just 6 numbers. For no crystal whatever could we find in any tables, and discussing with lots of people, looking online, looking in old books, all these 6 numbers. So we aren't able to say to an experimenter, take this crystal and we predict you'll see all these unfamiliar phenomena when you do the following experiments. So that's interesting, and there's some work to be done there in crystal optics. Now the third thing, which has come up very recently, and paper just published a couple of weeks ago about it, is this. Suppose you have a cascade of N conical refraction crystals. Well, why should you study that? Well, these people, Rafaelov and Abdelvan, have invented a conical refraction laser, where the lasing material in the cavity is a biaxial anisotropic crystal, and they claim this has properties which are superior to other lasers. I don't understand that. But anyway, in a laser, you back and forth, back and forth, back and forth, which is equivalent to having a cascade of crystals, and that prompts this analysis. Now, if you have all the crystals in the same orientation, having n of them is just like having one big one, nothing interesting. If alternately they're opposite to each other and the same strength, then what you have is that each reverses the effect of the previous one. That's what happens in the laser. But in general, if they're differently oriented, you get beautiful phenomena, which they're now looking for, actually. And here you can predict. You get a superposition of 2 to the n-1 double rings. Each of the radii of the rings is the sums of the sums and differences of the individual rings you would get from the individual crystals, and with strengths and phases depending on the relative orientations. And I've just got a few pictures of what you would see with a 3-crystal cascade there. I won't go into this anymore. So this subject is at a nice stage of development, and I want to finish with a number of morals one can draw, and there are really many of them, 13 of them actually. So here are the conclusions. Right. First of all, this led, as I've said, to one of the first, Hamilton's diabolical point, one of the first qualitatively new phenomena predicted by mathematics, conical refraction. It was, I believe, the first geometric phase. It was one of the original phenomena in singular optics. Over the recent decades, we've come to see that you learn a lot about light, indeed waves in general, by looking at their singularities, the caustics in optics, the phase singularities, optical vortices in scalar waves, polarization singularities. Well, this is one of the first singular phenomena in optics, polarization singularity, that I've already showed you. It gave compelling evidence that light was a transverse wave. This was still disputed, although people were getting round to the idea that light was a transverse wave in some kind of elastic medium. But with Hamilton's conical refraction, there was no longer any doubt. The only person who held out, surprisingly, was Brewster, who didn't like theory, and he still wanted to deny that light was a wave. But everyone else, immediately after Hamilton, was convinced. It was the first substantial application of phase space. I've mentioned that. I mean, this whole talk has been a kind of symphony of position and direction. The position where you look and the directions giving this conical intersection structure that underlies everything. You need the interplay of ray physics and wave physics to fully understand all the details of the rings and this axial spike that comes out at long distances. It led to unusual mathematics. I won't speak about that, but there's a bit of asymptotics which had never been appreciated before, which came out of this and which I realized was more general and wrote about. Now, it was the first conical intersection in physics, the Ur cone. Cones are very popular now. In chemical physics, for example, theoretical chemistry, you have the Born-Oppenheimer separation of the slow nuclear motion and the fast electron motion in trying to understand a molecule. And basically, you look at the, you freeze the nuclei and then solve the electron Schrodinger equation. And it turns out that in the space of positions of the nuclei, you get these surfaces, potential surfaces they're called, and where they have a degeneracy, the electron state, then Born-Oppenheimer approximation breaks down and interesting phenomena occur, which are being intensively studied. And now, recently, in graphene, the band structure of electrons in graphene, they're called Dirac cones, but they could also equally be called Hamilton cones. They should be called Hamilton cones. It's the same mathematical structure that's being studied. Now, the Paraxial Schrodinger, the Paraxial wave equation is isomorphic to the time-dependent Schrodinger equation for a particle moving in 2 dimensions. So all this exact solution for Belsky, Kappa-Luke, etc., for conical intersection also gives you something very precious. It's the exactly solvable model for quantum physics of a conical intersection involving time dependence of waves involving a conical intersection of the adiabatic energy level. So that's a nice thing to have. Extensions of the theory I mentioned, chirality, absorption, cascaded crystals. I didn't mention a nice contribution by Alan Newell. He's incorporated nonlinearity into the theory. The formalism is very beautiful. They haven't yet, him and, I can't remember, Indic, what they haven't done is to pull out qualitative consequences. You have an enormously long nonlinear crystal, and you would see effects due to nonlinearity and biaxiality that will be developed. It's a major contribution. It's a continuing stimulus for experiments beyond the ones I've mentioned. In particular, those effects I spoke about in the last few minutes should be identified. And now something else. The last 2 things, I'm going to touch on contemporary obsessions. This conical refraction, it's obviously fundamental in the sense that these singularities are at the very heart of crystal optics. But the conditions to see the rings are very special. It's hard work to actually shine this beam and so on. So probably nowhere in the natural universe does this phenomenon occur. Equally, nobody has found a useful application of it. So here's a phenomenon that's fundamental, doesn't seem to occur anywhere in the natural universe and doesn't seem to be useful for anything. Well, I rather like that. However, in the centenary year, this company offered $10,000 for the best application of conical refraction. They didn't get any takers, and so they didn't spend their money. However, now there begin to be applications. I mean, I mentioned this conical refraction laser. Whether it really is any use remains to be seen. James Lunny, John Donegan, the Dublin people are investigating whether the bright cylinder that comes out could be useful for optical tweezer experiments and might enable doing things that are less easy to do with the usual optical tweezers, which have a Gaussian beam or a Gauss-Laguerre beam. We don't know. That remains to be seen. But anyway, there we are. And my final comment is this, that there's a lot of fashion in physics. I don't think that's a bad thing. I think string theory is wonderful and people should study it. I think graphene is wonderful. Going back, I think high TC was wonderful. I think quantum Hall effect is wonderful. And it's right that thousands of people should swarm like insects onto a particular topic and write lots of papers. And the thing develops very quickly, and intellectually that's very worthwhile. But this hasn't been like that. And so you could say that this entire subject, that, as I've described it to you, is a 180-year or 2,300 moon antidote to short-term science. So thank you very much. Yeah.
approximately a conical wavefront in the natural universe, which is the gravitational lensing by what is called a singular isothermal sphere, which is not a bad approximation for the mass distribution.
Yes, I know. And you see that, I mean, conical wave is a different thing. You see it also in the Glory effect, the Brocken spectre. That also is a conical wave. But I agree, it's not the same thing. It's not due to anisotropy. And it doesn't have the same polarization structure as you go round. No, I know that, but thank you for mentioning it. Yeah.
And the other thing, sorry.
Yes, please.
In Raman's writings, he favored use of naphthalene, which apparently has a very large difference of refraction.
Yes, I know, and I've wondered why people subsequently haven't done that. He mentions this. Yes. He talks about it in some detail, how he makes it and so on. I know, but why don't people use it now? I don't know. Is it particularly difficult?
It evaporates. Actually, one project student working here did do that.
Was that recently?
No, when I was here, which is more than
that's recent.
15 years
Compared
ago.
On this scale, it's recent.
Yeah, right, yes. But the crystals all evaporated.
That was the problem. That's the problem. Okay. Yeah. If there's a write-up of that report, I'd like to see it, actually. Yeah.
The ionosphere, of course, is seriously anisotropic.
Yes, it's not switched on. Yeah. Take that one. Yes. Ionosphere is seriously anisotropic. Continue. Yeah.
Have you thought about any applications of this?
No, I know that. What is it? Ken Budden actually has written a great deal about optics in the ionosphere and anisotropy. I think most of the anisotropy there is uniaxial, so you wouldn't see these biaxial effects. Now, if it is biaxial, if I'm wrong about this, then you wouldn't see conical refraction exactly, because you wouldn't shine the light directly along. That would be very unlikely to happen. But still, there would be effects. But I think mostly it's in the ionosphere, it's mostly uniaxial. So it's a lot simpler than this, what I've described.
It would be in Ken Budden's book.
Ken Budden, yeah, it would be, yes, yes. Yeah, yes.
I just wondered, in the case of absorbing crystals,
Yes.
whether there are situations where the two eigenvectors coincide.
Oh, there are. Oh, there are. Indeed, as I'm often telling people who repeatedly rediscover this phenomenon, Pancharatnam wrote exactly about that. It's a very interesting case. And you get all kinds of, I mean, I give another lecture, different, called Physics of Non-Hermitian Degeneracies. And it's exactly that. There are whole areas of theoretical chemistry. Nimrod Moiseev at the Technion in Israel was the first person to tell me about this. I later found Pancharatnam's paper about it. He doesn't express it exactly this way, but it's what the effect is. Yes, there are effects, and indeed, I didn't have enough time, but those dark spots at the end, they are exactly places where you get the perfect parallelism of the eigen, and therefore you can get complete destructive interference sometimes. So it's exactly that, yes. And there are a number of effects in different areas of physics where this phenomenon, for example, just to say very quickly, if you have unstable lasers, that's a laser where one of the mirrors is reversed, so you explore the whole lasing cavity, then there's something called the Peterman Factor, which tells you the spectral line width of the laser divided by what you would get from quantum optics, the minimum, this Shafiloff-Towns. It turns out this is enormously broadened by in ways that were very mysterious. So you measure the line width as a function of for example, the Fresnel length of the cavity, for a parameter of the cavity. You get huge spikes. What they are is actually degeneracies of the non-unitary round-trip wave operator, non-unitary because you get light coming out of the sides, degeneracies in the complex plane of the Fresnel number, which are close to the real axis. And that's exactly a very major physical phenomenon. I identified it a few years ago, a major physical phenomenon associated with what you described. And there are a number of them. The experiments by Anton Zeilinger in atom optics in interacting with light also show these effects. So there are a number of them, yeah.
There are no further questions. It's break for tea. And we are sitting in about 15 minutes.
Is there a break for tea? No, there's not a break for tea.